some lovely reddish stars in the sky, but the only one we've ever seen is Star Mars. Star Mars.
But without spending too much more time, let me invite Simon Hayden to talk on TYCHOS.
Thank you, Gopi. I'll skip any further introduction because he made it so well. I mean, okay, so I'm Swedish and I live in Rome. That's all you need to know, practically. And also because I have the thankless task to try to summarize 12 years of research in 1 hour. So I'll be starting right away. And basically what I've done is I've retrieved Tycho Brahe's solar system model from oblivion, because it was an excellent model, and for some reason it was just swept under the rug or somehow completely ignored. It's now no one knows about his system. No one remembers how it was configured. And Tycho Brahe. So I mean, I would like to. Let's see. Oh no, this one. I would like to ask. Okay, so why have I put this first as a first slide? Because you have been watching this. You may be wondering, what is this complicated spirograph I'm looking at? Well, today, modern astronomers are, when they look up at the stars and they're looking for exoplanets and so on, they see this kind of patterns. This is modern astronomy for you. And below, this is what the TYCHOS model looks like. So, in these past years, I've been accused, by naysayers to, I have gone back, retrieving old things, obsolete, that have been disproven 1,000 times around. But it's actually the other way around. I could not have made the TYCHOS model like 20 years ago, because I've used many of the new discoveries to make it work. And I will explain it further on. So here we have Tycho Brahe, the loser, according to modern science, right? And Kepler, the winner, right? So I just want to do a little, I mean, you don't do this in science presentations, but I would like you to be honest. Okay, raise your arms, those who have heard of Kepler in their lives. Like 100%, right? Who has heard of Tycho Brahe? Really? Bit less, yeah. I tell you in Italy where I live, it's like 0. Tycho Brahe? What? Tycho? They don't know. In Italy where I live. In Sweden, there are more people that know Tycho Brahe, because it was actually on Ven, which is now a Swedish island. So Tycho Brahe is pretty well known, even by younger people. But Kepler is universally known. That's why I call him the winner, because that's what he is basically in modern science. But Kepler was, in 1987, he was proven, I mean, he was exposed as a fraudster. By whom? By the actual translator of his Astronomia Nova from Latin to English. He's called Professor Donahue, who is still alive. And it came out on the New York Times, and the first instance of an icon of science who has cheated, practically. I have no time to explain what kind of cheat it was, but it was pretty pretty bad. So already, I mean, Kepler, I am getting a bit irritated when I've read so many books in 5 languages. It always ends with Kepler saved the day and finally explained it all. But he didn't. He had to cheat. But we'll see why later. All right, so I should have said here, when Kepler, 26 years old, knocks on the door of Tycho Brahe, he walks in and says, okay, I'm a good mathematician. Is there any problem I can help you with? And Tycho Brahe said, yes, Mars. I have a problem with Mars. That was really, he couldn't understand what Mars was doing. So he gave him only the Mars observations, and Kepler said, I'm going to solve it in 8 days. Yeah, that's what he said. So why exactly were the motions of Mars such a troublesome problem? Before tackling this question, we must first take a good look at the currently accepted Copernican heliocentric model and compare it to Tycho Brahe's geoheliocentric model. Very few people today will know that Brahe's model remained the ruling model of our solar system for more than a century after his death, due to its superior accuracy, because he was much more accurate than the Copernican model before Kepler came and squished it into eggs and accelerating and decelerating planets. There is no variable speeds in the Tycho's model, and no egg-shaped orbits. No need for that. That's why I'm saying that the Tycho's model is a simplifier. And you could call me Simple Simon for that. So, do you still hear me like this? Okay. So this is what we've all been taught in school, right? A nice central sun in the middle, everyone in like a carousel, all around, very neat and clean, beautiful, very aesthetically pleasing. But with Earth then having to move at 107,000 kilometers an hour, you can feel it, right? You can feel the vibrations. 90 times the speed of sound. That's what we're supposed to do, folks. Have you ever given it a thought? Have you ever? We have life here. It's a special planet. We have oceans, we have life, we have trees, we have flowers. We have calm days most of the time. But we are going at 90 times the speed of sound. Really? Well, here was Tycho Brahe's model. He said that Earth was completely immobile, which is also a bit strange, because every single body in the skies has an orbit, whether a planet or a moon or a star, because also stars have local orbits, remember? Most people don't even know that. But the stars have orbits, and they all always have a companion. 95% of stars have a companion. We'll see that now. So this was his model, all right? What is striking here? It's the orbit of Mars is intersecting the sun's orbit, and he was laughed at by his peers. Oh, well, they're going to crash sooner or later. They're going to crash here, right? They're going to crash right here, bang, or here. No, because they're at the 2-to-1 ratio. So for two orbits of the sun, Mars has one, and they never crash. It's like a gearbox. And this is interesting because this is Tycho Brahe's model, okay? And this is Patani-Samanta's model. Considered the top Indian naked eye astronomer of all times. He also had no telescope. But he came to the exact same conclusion of the configuration of the systems with Mars and Earth intersecting. And you know what? This I found by chance in a book which an Indian astronomer gave me, an old Indian astronomer in Bangalore. When I went to visit Gopi, he gave me one of his 4 books of Indian astronomy, ancient Indian astronomy. And I opened it, and I thought, wow, this is exactly Tycho Brahe's model. So I had asked about who is Patani Samanta and so on, but no one knows him in the West, right? So anyway, they came to this saying, these two great, I mean, Patani Samanta is one of the greatest observational astronomers in India, and Tycho Brahe is probably the greatest in Europe. So these are not, you know, anybody's. I mean, they are important guys. And they came to this same conclusion. So here is, this is not my diagram. This is taken straight from an astronomy book, and where they show, you know, a classic binary system should look like this. I just put, you know, let's say that this is the sun then, and let's say this is Mars. This is what at the beginning of my reasoning 12 years ago, you know, started learning about binary stars. And I said, well, what if Earth is here, you know, in the barycenter? So what I'm saying here is what Tycho Brahe and Patani Samanta had unwittingly discovered was that we live in a Sun-Mars binary system. So I postulated this and went ahead and tried to verify this step by step for 12 odd years. And it's been going very well. So, a legitimate question to ask, if 85% of the stars were considered binary actually in the 80s, 40 years ago they were saying 85% of the stars are binary, why couldn't 100% be binary? And if 100% of the stars are binary, then our sun can be the only bachelor in the universe, right? The only poor bachelor. It would be absurd to think, statistically speaking, that the sun is the only single star in the universe. So what do we have here? Here we start seeing, you know, modern science journals. This is from 2017, so, you know, a couple of years ago. And new evidence that all stars are born in pairs, right? Stars like our sun are always born with a sibling, astronomers say. In the case of our sun, that twin has long since vanished from the neighborhood. Well, it's gone away. Ciao, ciao, bye-bye, I'm going. Yeah, we were nice friends, but, you know, poor sun. Maybe he's a cornuto as well. Somebody nicked his wife. Anyway. But in later years, evidence in support of this proposition that all stars are binary, which means that it only means that all stars have a companion, much smaller usually, or even the same size, but often much smaller, and so small that it can be even detected. That's why maybe these 10, 15% that they think are single stars are just because they haven't found a small companion. But we have been found, I mean, they have been, not me, I don't have these enormous observatories, but the great observatories keep finding more and more binary stars every day with this new technology called adaptive optics, because that is what they use to, they can actually create an artificial star to help them see and focus, and if the star was seen like this before with adaptive optics, oh, it was actually two stars. We were seeing this before, like in the 1990s we saw this, but now in 2020 we see this. So here is the first, yeah, I mean, this is a clean portrait of the TYCHOS model, just to make it simple and to the basic configurations. I mean, the two main players are then, as I said, the sun, correct? The sun, and here is Mars, okay? All right, here's Mars. Okay, so you see, the sun has two moons. Moons? Aren't they planets? No, they are moons. Venus and Mercury are moons, and I'll show you why. Mars has two moons, so it's a nice couple. Both have two kids. Mars has two moons, and the Sun has two other moons. Very balanced little family. And here I say, I want to say strongly, Venus and Mercury are evidently the moons of the Sun. We must call them moons in any way. If it's just a question of semantics, but they are moons because we can define a moon as a body that spins around its axis at walking pace. Only Venus and Mercury spin at 2.7 kilometers an hour. That's Venus, and Mercury double that. And our moon, 6 times the speed of Venus. So it's a 1-2-6 resonance between our moon and Venus and Mercury. So, you see the similarities between Venus and Mercury and even our moon. Our moon only spins a little bit faster for some reason. But, and then, what does NASA say about the fact that Venus and Mercury are moonless? NASA says why Venus doesn't have a moon is a mystery for scientists to solve. Yeah, they haven't solved it yet. They don't know why Venus and Mercury are the only planets without moons. What is my answer? Because they are moons. They have no moons because they are moons. And we have never seen a moon with a moon around it. No, don't laugh. Even Wikipedia says that. Until 2021, no moon has ever been seen going around another moon. That's official. Okay? It's not me making up things, I don't like to make up things. So, in the TYCHOS model, the Sun and Mars are binary pairs circling around each other at a 2-to-1 rotational ratio. As I just started this presentation, I told you this. It's a 2-to-1. It's actually, people will say, no, it's 2.1 to 1. Well, over a long time, this will equalize to 2-to-1. Over long periods, it will be exactly 2-to-1. So here, this is the main drawing that I came up to when I had come further in my research. And in 2008, my first book came out. And I had come this far. So I said, let me print a book about at least these basic things. But then I spent another 5-6 years trying to verify this and going back, reading all kinds of old experiments that ended in, we see some kind of discrepancy, but we don't know why. And there were many different experiments, like, Michelson-Morley experiment. They couldn't measure the speed of Earth. The ether wouldn't respond. Einstein came and said, there is no ether. We can't. There's no ether. Einstein just said, there's no ether. You can't. That's why you can't measure the speed of Earth around the sun. But, it's full of funny things in astronomy history. Okay, so this is, I just said this. Venus and Mercury are the moons of the sun. Just like Phobos and Deimos are the moons of Mars. The Earth revolves around its PVP orbit. So now we get to the PVP orbit, which is basically my own contribution to Tycho Brahe's model, which was almost perfect. He only needed to. I'm sure if he had lived a couple of decades more, he suddenly died at 52. Apparently, well, we don't know how he died, but that's another story. PVP orbit, what is it? Well, it is the Earth's orbit, but the Earth is moving at the snail pace of 1.6 kilometers an hour, according to my calculations. I came to this because I postulated that this orbit is the great year, the famous time of the precession of the equinoxes, which officially is about 26,000 years. And gradually I came to a more precise number, 25,344 years. So it takes 25,344 years to make this one, okay? So please don't think that we are going around the Mars, because that's the first thing to say. this is kind of a virtual orbit we see here. It needs 25,344 years. The whole system will rotate clockwise and will make Earth being dragged around this central orbit. All right? So it's never going around. We'll see why Mars is in the middle. Mars passes in the middle, exactly, of this orbit, which is 113.2 million kilometers. When Mars comes closest, it's at 56.6 million kilometers, and that's officially, that's what they say. I mean, that's what we know. So this was something I found later. Long after I had calculated the PVP orbit, I realized that Mars, when it comes closest, passes right at the radius of it. This is the radius. This is when Mars passes closest. It just happens to be at 56.6, which I fell off my chair, you know, when I noticed that. So here you have to imagine you're coming in a spaceship, you know, in Star Trek spaceship, and you're coming. Oh, look, you see. Oh, here is the Earth-Sun system. You see it from the side, right? So here we are today on this side of the PVP orbit, and we have Polaris as a north star. Our south star is Sigma, or Tantis, right? And we simply go very slowly around this PVP orbit. Here is a bit larger, so you can see how it moves. Basically, if you want to show this to your kids, you take a globe in your hands, in your living room, you tilt it 23 degrees, and you show, now we are under Polaris, okay? now 12,000 years later, we are under Vega. And then we're going back to Polaris, PVP, PVP. That's why I call it that. That's my name, PVP. All right? Oh, and of course, you know, I should have shown you, in 12,000 years, we will be under Vega and over Columba. There will be a southern star in about 12,672 years from now. Here we see it in a different way. So, I mean, here we see three, pieces of cake of this great year. This is what I just showed you. I mean, now we are here. So, in June 21st, we are facing Gemini constellation. 2,112 years ago, we are facing Cancer, and in 2,112 years, we will be facing Taurus. We're simply going around this ring. Simple as that. And that is the precession of the equinoxes. You know how official astronomy explains the precession of the equinoxes, which means to explain why the northern stars change over time. And no, they say that although the Earth spins anti-clockwise, and although it goes anti-clockwise around the sun, it has a small wobble that goes the other way in 26,000 years exactly. You know, it slowly kind of wiggles, and goes the other way. That's what we're told at school. That's what they teach in astronomy school. Isn't this much more logical? We are lying. Why are we lying this way? Probably because there's much more landmass up here. So maybe for some magnetic reason, we are always looking at the sun outside towards the sun's orbit, which goes around. So that's why we're lying like this. That's just speculation, okay? I can speculate sometimes, right, without being laughed at. All right, hopefully. Okay, so this is not my graphic. This is from an official astronomy book. This is how they show how we change North stars, right? So, how does it work? So now we are here under Polaris. This is looking up in the sky, okay? As if we look, from Earth. And okay, so now it's Polaris, and you see here it goes anti-clockwise. Yeah, but that's because we're looking from below. This will reflect as a, This will reflect as a clockwise ring, which is a PVP orbit underneath, right? If we swap this. So this is how, I mean, this is officially accepted, that we will be under Vega around 12,000 years from now. And we were under Tuban during, Egyptian times. They left, documents that show that Tuban was the northern star like 5,000 years ago. So we know that much. So Kepler's one and only task, to figure out the puzzling motions of Mars. And he said, I should figure it out in 8 days. Well, 8 years later, he was still working on it. And he fudged probably, just got frustrated and said, I must do something. So he invented all sort of, squished the orbits, made the planets accelerate, decelerate. Very clever. But that's only mathematical mathematics. He was into mathematics. That has no relation to reality or observation. What he did is just a mathematical construct. And he made it kind of work, but you'll see that doesn't work at all, in fact. So this is just to answer, the knee-jerk objection. Yeah, but is Mars supposed to be a planet? Haven't we heard little planets? It's a planet, Well, first of all, Mars is the only reddish-brown planet we have, right? The only one. And you know what? Brown dwarfs are in fact reddish-brown, reddish-orange. But even better here, this is a very recent journal that says this: Can a star turn into planet? By Christopher Baird. Yes, a star can turn into planet, but this transformation only happens for a very particular type of star known as a brown dwarf. Right? Despite its name, a brown dwarf that is still glowing does not appear brown. Rather, it appears magenta or reddish-orange. Sounds like Mars to me. Could be Mars. Mars has this color. Despite beginning life as a star, a brown dwarf quickly uses up its heavy hydrogen, goes dark, cools, and spends the rest of its life as a planet. That's from an official science journal. It's not me making this up. Okay, but this is very funny. First time I opened Kepler's Astronomia Nova, I went page 1, page 2, page 3. In the first few pages, you have this drawing here. This is Kepler's drawing, one of his attempts to understand Mars. But he ditched it. He didn't like it. But you know what? That was at the time we had already, with my partner Patrick, which I want to cite because Patrick Holmquist is a computer programmer who has helped me make this simulator, which we will look at later on. We have a simulator showing exactly how the system works, and it works. So this is from the TYCHOS, the TYCHOS 3D simulator. So what is this? What did he write here, Kepler? From 1580 to 1596, this is how Mars moved, according to his calculations, using Tycho Brahe's tables. All right, so I put Mars here in 1580, and I made the machine run, and it ends up here in 1596. It's exactly superimposable. The machine simulates the man. This is Kepler, and this is a machine, right? So the most ironic quote from Kepler ever. By the study of the orbit of Mars, we must either arrive at the secrets of astronomy or forever remain in ignorance of them. Yes, well said. We will remain in ignorance if we don't understand Mars. So here are the facts. Here are the facts which Kepler had to cheat to kind of circumvent and make things work. The facts are that, let me try to explain this, a bit graphically. Let's say you're in your garden, all right? You have a telescope, and you see Mars coming one day, and you have your favorite star, and Mars just, conjuncts with your favorite star. So you say, okay, that was beautiful. Let me wait till it comes again. You will have to wait 707 days to see this thing reoccur. And then again at 707, 7 times. 1, 2, 3, 4, 5, 6, 7 times. You will have to wait patiently 707 days to see the same thing happening again. Mars aligned in front of your favorite star. Let's say Sirius, just to give it a name. Well, if you're not, if you don't know it, you will miss the next passage, because the 8th passage will happen only in 546 days. Wow. Why would that be? Isn't Mars in the 4th lane going around us in the 3rd lane? How could this possibly happen? Well, Kepler completely ignored these empirically observable facts and instead averaged the sidereal period of Mars to 687 days. Yes, but never does Mars realign, reconjunct with a given star in 687 days. It always does this, all right? This is what it does all the time when it repeats. This is the 15-year sidereal cycle of Mars. You can't deny it. This is, all astronomers will know that, but they don't talk about it much. That's the thing. They don't talk about it. So here is from a Copernican simulator. This is not the TYCHOS, okay? This is with the sun in the middle, right? This is from the sun in the middle, okay? Got it? And on November 5, 2018, Earth had Mars here, and conjuncting with star Denebal-Jedi, which it chose randomly, like a control star for this experiment. Well, after 546 days, according to the Copernican model, we would have done then 1 year and a half, because 546 days is 1 year and a half, right? So 1 year and a half, and we would be on the other side here. We would be on the other side, so we would have moved by 300 million kilometers sideways. But on this date, May 4, 2020, Earth and Mars were again realigned with Denebal-Jedi. And these are parallel lines, folks. These are, at least on a very large resolution computer, they are pixel by pixel. Okay, so how do astronomers explain this? How do you explain this? Well, they'll tell you, that's because 300 million kilometers is nothing. It's nothing. It won't make any parallax change. And the stars are so far away, so it doesn't, what? That doesn't matter. It has nothing to do with the stars being far away, first of all. If the point of light is there, it's there, it's going to be there, it's never going to be there. This point of light is there, and then you have Mars, which is much closer to your nose than that star. Well, obviously, there will be parallax if you move just one step. You won't have the stars in line with your nose, which is Mars here in this case. But think about moving 300 million kilometers sideways. This can't happen, right? This can't happen in nature. It's impossible. That's why I dare write the word geometrically impossible. Oh, okay, so here is another Copernican simulator. And you know what? What is this? What is this? This is the long sequence, a 15-year sequence. 7 times 707 days, and the 8th time 546. This is how it looks like on a Copernican simulator. So, first of all, none of them are the same. They always, you see, Earth and Mars, Earth and Mars, Earth and Mars, Earth and Mars. Okay, I should use this. You see, these are all conjunctions with Denebal-Jedi, my control star that I used, right? And mind you, the most distant ones, 7 and 8, they represent the short ESI, the short empirical sidereal interval, which we saw before, which Maya knew about, actually. If you ask me how I found it out, how did I find out these numbers? Well, they were in a very hard-to-find study of several astronomers who had studied the Maya astronomy, which knew these precise numbers. Okay, but look at this. None of them even matches the other, but they should point to the same place, right? Well, are you ready now? Are you ready to see how the TYCHOS handles this? because I wasn't even ready. There again, I fell off my chair. And I was trembling when this was when I was testing the new simulator Patrick had, fixed, and we had come to some kind of accuracy. Here is how it works out in the TYCHOS simulator. Do you understand this? Well, I explain. These are the 8 conjunctions. They are all on the same line towards the star, logically. All these 8 conjunctions, which are the same as we saw before, same as this. And on the TYCHOS, they are on the same line of sight. Right? All 8 of them, including that short one, 546. So this is, to me, this is ultimate proof. I don't care if you think I'm boastful but this you can't just debunk this. This is what we see. This is not debunkable, not disprovable. So why does it come back in 546 days sometimes? You must have asked this question right now. Well, it's because since Mars does this funny spirograph, and you see each time it does this loop, it goes backwards. That's the retrograde motion. But it does that physically. It's not an illusion. It's not because we overtake it, as they tell us. It's because it actually does it, because geometry does that. It's what a revolving object that revolves around another revolving object will do if it's magnetically attached or whatever. I mean, we still have to understand why. But if you attach a yo-yo string to the sun, and the thing on the outside will do this. Right? So why does this 546-day period occur? Because on the 7th time here, when it comes here, it is finished. It's just finished doing its loop in front of that star. Okay? Just finished doing this loop. And so we start here, day 0, and it only takes 546 to come back to this line. Okay? And that's the line that's a famous line we have here, this one, right? That's why 1 out of 8 times we have these shorter periods. There's no rival to this. There's no other model that even can compete with this. Or if you have it, please, if you have planets moving in triangles or squares, you're welcome to come up with one. Oh, and this is such a beautiful thing. I mentioned briefly this before. So when Mars comes closer to Earth, it comes at 56.6 million kilometers. And that just happens to be exactly the radius of my PVP orbit, which I calculated separately for other reasons. Well, for reasons that I've skipped explaining how I did it, but it's in the book. By the way, there are 4 books only, so out there. So if you want one, you will have to rush. So here, look at this. Isn't this beautiful? So it turns out that the orbit of Mars pivots around the center of the PVP orbit, which means around the center of the whole system. These are 4 superimposed screenshots distant by 6336 years, 1, 2, 3, 4, just superimposed, and at a time when Mars passes in the middle. So this is what it looks like. Over 25,344 years, will look like, if you take a time lapse, you're in a machine above our solar system, this is what you will get. A time lapse which leaves the lights. Yeah, this is what you will get. And the center, people always ask me, so what's in the center of the PVP orbit? Why is it nothing? Is there anything in the center? Well, I don't know, but Mars evidently always passes there. So Mars must be an important thing. It's not just any planet. Mars is like the pivot. mean, we still need more time to understand why this occurs, of course. But this is absolutely consistent with everything, all the planets in our simulator are the correct distances, correct ephemerides, they're pretty much almost perfect now. I mean, you can compare the stellarium, the famous stellarium with our TYCHOS pretty well. There are some minor discrepancies, but really tolerable. So now I want to talk a little bit about Sirius, because Sirius is a serious matter. Yeah, it is. I'm sure you will agree. So when they discovered Sirius B, the little, they call it the pup, actually, this little thing here, in 1856 sometime, they were shocked. All astronomers were shocked. What? What is this little thing doing there? Now, how come it goes around this huge star, Sirius? This is the brightest star in our sky, right? So Arthur Eddington, this is what he said. The message of the companion of Sirius, when it was decoded, ran, I'm composed of material 3,000 times denser than anything you will have ever come across. A ton of my material would be a little nugget that you could put in a matchbox. The reply which most of us made in 1914 was, shut up, don't talk nonsense. I mean, this is like, he's making serious talk here, you know. The message at Sirius B, it was nonsensical. So what did they finally come up with, modern astronomers? They said, oh, Sirius must be extremely dense, must be very heavy. It's small, but it must be extremely dense. You know what they say? You know what they're saying today? This. On Sirius B, the force of gravity is 400,000 times stronger than on Earth. That's what you can read in textbooks today. Why would it be there? I mean, how did they find out? Oh, because they have to make the laws of gravity function. They can't, you know, it's very tiny, but it needs to be heavy to be there. So we just say it's very heavy, it's very dense. Oh, well, but that's not how science works to me. You don't just patch up with ad hoc ideas. I mean, we haven't put Sirius B in a bathroom scale, have we? To see if it weighs more or less. Right? Have we put the sun in a bathroom scale? No. But we do say that the sun is made of the two lightest gases in nature. Helium and hydrogen, 98%. So why couldn't the sun, for instance, weigh the same as Mars? Mars is only 205 times smaller than the sun. Not more than 205 times smaller, which we will now see. Here we go. So what I found out also in the early stages, the early years of my research, I was curious to see how big is Sirius in relation to its mother, Sirius B. Well, it's 205 times smaller than it's, okay? 205, that's what they say. I mean, you can go to Wikipedia. It says that Sirius B is 11,700 kilometers wide. That's just like same size as the Earth, almost, right? And Mars is also 205 times smaller than the Sun. Coincidence? Maybe. Coincidence? All right. Well, here is more coincidence, if you like. So this, to the left, the white graphic is not mine. It's from an official astronomy book. One of the few who finally showed me what they say that Sirius A does. Well, it does this. Usually they just put Sirius A like a dot. But here they gave also its orbit, which is small, right? Like the Sun, which is smaller than Mars's orbit. And then they show Sirius B, which goes, mind you, it goes the other way than so it goes clockwise, right? Which is much bigger. And then this is me. I put Sirius C here just to make a point. We have not found Sirius C yet, but there are many studies who say that it should exist, but it's blinded in the glare of the big Sirius A. But they can't see it telescopically, but they see there is some wobble that suggests that there could be the Sirius C. And they say it should be slightly bigger than Sirius B. What is Earth? Earth is just double Mars. Earth is double the size of Mars. So do you see any similarities between these two systems? I mean, we even have the perigee of Sirius B at 1 here, and the apogee at 7, like a 7-to-1 ratio of how far you can get to the center here. That's exactly what we have in our system, 1 to 7. My goodness, that's also similar, right? So about our moon, okay, we already know that our moon is a unique and exceptional lunar satellite. It's very big, proportionally to its host, almost a third of Earth. And the funny thing, people don't talk much, I mean, the astronomers don't talk much about, is it revolves around Earth and rotates around its axis in 27 days in synchrony with Sun's actual rotation. So we have the moon going around us at the same time that the Sun rotates around its axis. That's a Carrington number, 27.3. So we have lots of coincidences going on here. And this is probably the most beautiful thing. I mean, it's, you've got to say we live in a Swiss clockwork at this point. Because, as I told you about the Maya was really, that stuff I read about the Maya was fundamental for my research. They used the synodic period of the moon for them. The best average they came to was 29.22 days. So, what am I saying here? I'm saying that our moon is our system's central drive shaft. How can I say that? Yeah, because the moon has a 29.22 synodic period. That's the time it takes to return facing the sun. If you multiply this exactly by 4, you get Mercury's period, 116.88. By 20, 584.4. By 25, you actually get Mars sidereal period, not synodic, but it's 25. But then you get 150 Jupiter, 375 Saturn, 1050, 2062.5 Neptune. Neptune is a bit of a crazy guy. And Pluto, 3100. They are round multipliers of 29.22, all of them. So if you would have to construct a clock of this, it would be very easy because you just put gears which are just a bit bigger. You can do a very simple clock with this. The Antikythera that they found, they're thinking that I had to have so many gears, we can't find them. The gears must be lost. The Antikythera they found in well, maybe the Antikythera was much simpler and they only needed a few cogs, 8, 16, whatever. So about the NLM, I only have little time left, so I have to rush. The NLM and the man's yearly path. So the NLM is what the sun does in 1 year. If you are a photographer, take a picture of the sun every 10 days, you'll get this H shape. That's okay. So the sun is up there in June, and it's down there in December. That's no mystery. But why does it sideways? Why does it wiggle like this? And why is it 3 to 1? Why? That was something I didn't solve for years. I just couldn't wrap my head around it until I realized that a man on Earth. Now, please understand, we are looking at Earth as from the North Star, as we are on the North Star looking down on Earth. Okay, so Earth goes slowly from left to right at 1 mile per hour all the time, while rotating. This will cause, I promise you, this will cause a man, which here is London, okay? Let's say this man in London starts looking at the sun in September, October, November. The sun is going around us, okay? So September, October, November. If he stands still in London, he will do this, the man's yearly path. he will physically do this while he, and also when he watches, when he looks up at the stars, he will do that. And I will go quickly forward to show you that even this. So this is hard to explain now in a few minutes why this will produce this age, but you will see that it works if you take care, care and read the book. But this is what James Bradley saw. He was looking up. He had put a telescope in his chimney, and he stood there, and he looked at the star Draco, and he said, "Wow, how funny! It moves completely in an unexpected way because it does, like this." And so he invented the aberration of light, which is the most incomprehensible excuse for explaining why the stars move like this. He said, yeah, because when the rain falls, it rains, and so it's like the light particles. When the light particles fall obliquely, then we will have to expect that. I don't know. I swear, I've tried to understand what it means by the aberration of light, but it's impossible for me. I'm not smart enough. So this is instead, what is it? This is this. He was looking at, and then he said, okay, his favorite star, Draco, was doing this, but then he looked at the other stars. All the stars were doing this. So what would has his logical conclusion have had to be? That he's doing this, not all the stars, right? That would be the most elementary conclusion to do. He didn't do it. Here he is, wiggling around there. What? James Bradley here. What the heck? What's going on here? All right? And this is from an official astronomy journal. This is what Star Vega does in 3 years. And Star Vega is very straight up, it's the northern star, circumpolar star. That's why it will be neatly like this. Just like this, the trochoid. This is called a trochoid, by the way. Or a cycloid. And Proxima, which is our closest star, right? But Proxima is not up there, it's down there from our horizon. So that's why this is a bit flatter, okay? This thing is flatter than this, okay? But that's just a question of perspective, Depending on where the star is from our equator, it will do, it's strange, a bit different loops like this. But it will do loops, because we're going slowly forward, rotating all the time. Simple. Simple. Okay. So about star distance and stellar parallax. Well, you know what? I'm going to skip star distances because it always brings up. But I'm saying that the stars are much closer. I'm not sure if they are exactly 42,000 times closer, but I still hold on to that theory. But it's because, since we measure, usually astronomers take 6 months, then they take a picture of a star, wait for 6 months, another picture, and they say, oh, wow, that star must be very far away because I've moved 300 million kilometers sideways, So that star must be extremely far away. No, but in six months in TYCHOS, we move only by 7,000 kilometers, which is 42,000 times less. So I'm postulating that the stars might be 42,000 times closer. It's not as crazy as it sounds. But this is more, concrete facts. I mean, this is more verifiable. They have a problem. Astronomers have a problem today. They keep seeing negative parallax, which is unphysical in their paradigm. There cannot be any negative parallax in the Copernicus system. Because this is I've done this little cartoon here. The car going around, just like they say we go around the sun, okay? This is the Copernican system. Well, we could only ever see out from a right-hand window, a nearby star. So imagine going in the car, you have a trees going by. So you go in the car, look out the right-hand window, the trees would always go from your left to your right, okay, in this case. But if you look out this, you can't look out the left-hand window because that sun is always there. But here, You can. Because it's the sun going around us, and then we will alternately be able to look out both windows. And therefore, we will find negative parallax. Yeah. We're almost ready. So, in the TYCHOS model, any given star can exhibit either positive or negative parallax, depending on the time window chosen. And you know, that also has to do with the mass-Rayleigh path. It gets a bit more complicated exactly to say, but we expect negative parallax in the TYCHOS model, whereas astronomers are trying to truncate their negative data. They discuss between themselves, how come we have so many negative parallax? We have to do something about this data. We have to truncate the reports. They're truncating the negative parallax data as if you could just throw them away because they don't want to have them. And you know, the funniest thing, the man credited to have found the first ever stellar parallax, this man, Friedrich Bessel, you know what I found in an old, not so old, book from the 50s maybe, by Anne Blair. She says, she's a very good historian, she says that the first time Bessel reported, he said the first time he had he was looking for the parallax of star Cygni because it placed well for him. And the first attempt, he got a negative parallax. So he was frustrated, and Bessel was disappointed again, but he persevered and finally found the positive parallax. So here I explain, and fortunately, I found the time period he chose in another book. So see what happened. And we can reconstruct what happened. So Bessel, first time he tried, it was between August and March. August to March, right? So you see he's gone backwards here. Because he has gone backwards. So he will see Cygni with a slightly negative parallax. Second time he tried, he did it between March and July. And here he's properly going the right way. So we will get the positive parallax. That's why this happened. And I can reverse engineer even those mistakes they made. But and this is the same thing, just to have another example. All of the top astronomers first tried Sirius, because Sirius is the biggest star, to see if there was some parallax with Sirius, okay? Masculine, this and that. I mean, all the best of the day, Frenchmen, Englishmen, Germans, and they all disagreed because so in fact, when some of the top astronomers of this world tried to determine the parallax of Sirius, some found it to be 8 arc seconds positive, and others found it to be minus 2.5 negative. How could that be? And they argued and argued and never solved the problem. But it's written in the books that this happened. Nobody ever solved this. Well, see what we have here? Probably some of them used this period from March to September, right? Or to March or whatever. At least it's kind of 3 times this. It's 3 times positive here and 1 times negative if you use this period from September to March, because you're going backwards, right? Here you're going forwards correctly, I mean, as they expect, and then here we're going backwards. So 3 to 1 is like 2.5 times 3 is almost 8, right? So it's kind of 3 to 1. Yep.
I think we have to pause here.
I have finished. I've actually almost finished. 3 minutes more?
No, actually.
Okay.
Already 5 minutes over.
Okay. So anyone who wants to see the simulator at play can walk in that room later. We have a screen to see the TYCHOS in action. Okay? Thank you.